Okay, so today we're going to be talking about resonance in an RLC circuit. But before we get to the whole resonance issue, let's just kind of go over what is an RLC circuit. So an RLC circuit is just a simple circuit. It has three basic components. There's the resistor, that's the R. The L is actually an inductor, and the C is the capacitor. So it has these three components. They're all in series, and then flowing through these components is an alternating current, or in other words, AC. And that's going to be important that the current is alternating at some frequency, and also that they're all in series, because that current, as we know from Kirchhoff's laws, if it's in just one loop there, the current is going to be the same throughout the entire circuit. Alright, so now that we have a basic idea and a visual of what is an RLC circuit, we're prepared to discuss how are these individual components going to act in this circuit. So the resistor in the RLC circuit, we know that because there's an alternating current, the voltage across the resistor and the current flowing through the resistor are going to be oscillating constantly, just back and forth, up and down the whole time. And according to Ohm's laws, if those two are changing, then it's possible that the resistance that this resistor is applying could be changing as well. However, if we look at this graph on the left side of the page here, we see that as the current changes, the voltage is changing at the same rate, or in other words, the voltage across this resistor is changing in phase with the current passing through this resistor. And what that means is, since they're both basically changing at the same rate and the same pattern, the resistance is going to remain constant the whole time. And that's important because that means that the resistance is not dependent on frequency. And when we start looking at resonance in the circuit, it's going to be important to figure out, is this going to be dependent on the frequency or not? Okay, now that we understand a little bit about how the resistor is going to be acting in the circuit, let's look at the inductor. So because of the alternating current, the voltage across the inductor and the current passing through it are going to be changing constantly. And if we look over at the left side of the graph here, we see that as the current changes, the voltage is changing at the same rate. It's following the same pattern. However, it's just doing so 1/4 of a phase before the current changes. And that's because this inductor, just the definition of inductor is something that opposes change in the current. So anytime the current's changing directions, this inductor is going to induce a current going the opposite direction just to try and balance that out. So it's basically acting like a resistor. And that is a characteristic that we call the inductive reactance. And it's that variable x of L that you see there on the right side. It's in units of ohms because, like we said, it's acting like a resistor. And it can be calculated using this formula there at the very bottom of the page. If you know the frequency of the circuit and you know the inductance of the circuit, then you can calculate this characteristic inductive reactance. Alright, so now let's look at the capacitor. So with the alternating current, the current and the voltage are going to be oscillating, changing directions through the capacitor. However, we know that from when we study capacitors, we know that as the capacitor charges and discharges, it has the ability to slow down or even stop the current when it's completely charged. So again, it's acting basically like a resistor. And that's dependent on the frequency. So both the inductor and the capacitor, we know, they're both frequency dependent. And if we look on the left side here, we see that just like with the inductor, the voltage and the current on this capacitor, they're changing at the same rate. They're following the same pattern. However, on the capacitor, the voltage is changing 1/4 of a phase after the current changes, whereas the inductor was changing 1/4 of a phase before the current. And just like with the inductor, we have a value here that we call the capacitive reactance. It's the X of C that you see there on the right side. And we can calculate that if we know the frequency of the system and we know the capacitance of the system. Then we can use that to calculate this capacitive reactance, which is basically just a value of how is this capacitor going to react to try and impede the current or impede the change of current in this circuit. Okay, so now it's time to try and put all these components together. So if you remember from when we talked about the inductor and when we talked about the capacitor, we were looking about how their voltages were changing. And we said that the voltage on the inductor was changing 1/4 of a phase before the current, and the voltage across the capacitor is changing 1/4 of a phase after the current. If we superimpose the graphs of those two on top of each other, we see that when the voltage across the inductor is at its minimum magnitude, the voltage across the capacitor reaches its maximum magnitude. And what that tells us is that these voltages are actually either partially or completely canceling each other out. And that's going to be important when we want to learn about the resonant frequency of this circuit. So we know how the inductor and the capacitor are going to interact, but now let's put it all together and add the resistor in as well. All three of these components, they can act to impede the current. So what we can do is we can basically calculate what's kind of like an overall resistance of the circuit. And that's what we call the impedance of the RLC circuit. It's denoted by variable Z. We can't just add together all of those because the resistance from the resistor, that's constant, but the other two, those fluctuate depending on the frequency. And so we have this special formula down here at the bottom that we use to calculate this impedance or like this overall resistance of the circuit. And this formula is going to become very important for us when we want to think about the resonant frequency that this circuit's going to have. All right, so based on what we know about the impedance of the circuit, we can use that to calculate the resonant frequency. And the resonant frequency is the frequency at which the inductive reactance and the capacitive reactance are equal and opposite to each other, or in other words, the difference between them is 0. So we can set those two equal to each other, and then if we substitute in each of their individual formulas and we solve that for the frequency f of O, we are given this formula for the resonant frequency. And so that's going to be this resonant frequency is equal to 1/2 pi times the square root of the inductance and the capacitance of the circuit. So that's kind of how we reached the formula for resonant frequency mathematically, but let's just kind of talk about what resonant frequency really means. Why is it important? Why do we care about it? So when we're talking about resonance in these RLC circuits, these are some of the characteristics that you'll see. The effects of the inductor and the capacitor are going to cancel each other out. And what that means is that those induced currents going opposite directions, at this resonant frequency, those are going to completely cancel each other out. So the only resistance that we're going to have in the system is just going to be that minimal amount of resistance provided by the resistor. That might just even be like the resistance from the wires in this circuit. And when we're at this resonant frequency, that's what we call like the natural frequency of the circuit. This is the frequency at which the current would oscillate in this circuit if there wasn't some sort of external voltage forcing it to go at a certain frequency. And this is going to be more important when we think about the real life application. So we're going to go through an example with a radio and see how the resonant frequencies are important when we're talking about radios. Okay, so when we have a radio, we know that we have this little machine, we tune it to a certain frequency, and then we hear music or the news or whatever. But in terms of an RLC circuit, actually that's what a radio is, or at least the receiver part of the radio is. And the radio receiver works best, it's going to have the clear sound and everything, when it's tuned into the resonant frequency of that circuit. So you might ask the question, well, if there's just this one resonant frequency, how can we tune into so many different stations? And the reason is because we can have these variable capacitors inside the radio. Basically, the inductance of the circuit, that's going to be some sort of constant that we're not going to be able to change, and we can't change the frequency because that's what we're tuning into. But we can change the capacitance of the circuit based on the capacitor itself and how far we move the plates away from each other. And so that's going to become even more apparent. We'll do a little practice problem here where we work through it and we see how changing the distance between the plates allows us to change in between stations or frequencies on the radio. Okay, so let's take a look at this practice problem real quick. So it says your radio, whose capacitor's plates are 10 centimeters apart, is tuned into a station which has a fundamental frequency of 100 megahertz. However, a song we don't like comes on, so we're going to have to change the station, obviously. So when we turn the knob, changing the stations is actually changing the distance between the plates of the capacitor. So if the new station's at 150 megahertz, how far apart are the plates of the capacitor? Okay, so let's look on the right side here. That first equation is for the fundamental frequency. And we know that the only things that are actually really changing in these equations is the fundamental frequency is increasing. We're tuning into a new one. And we're changing the distance between the plates and thereby changing the capacitance. So it says our original one is 100 megahertz and we're changing that to 150 megahertz. So that's increasing by a factor of 1.5 or 3 over 2. So that means we're going to take the left side and increase that by 3 over 2. We know that that means that the right side of the equation also has to increase by 3 over 2. But the capacitance is on the bottom of the equation and it's underneath a square root. So that means we're going to have to increase it by a factor of 2/3 squared. So if we take that 2/3 squared and we put it into the second formula there, then we can figure out how much the distance is going to have to increase. So if the capacitance is increasing by a factor of 2/3 squared, then that means that the distance is going to have to increase by a factor of 3/2 squared. So if the distance has to increase by a factor of 2.25 or 9/4, so if our original distance was 10 centimeters, then we take that, multiply by 2.25, we get 22.5 centimeters. That means that if you want to change from our original frequency of 100 megahertz to our new frequency of 150 megahertz, we're actually going to be increasing the distance between those plates by 12.5 centimeters. Alright guys, well thanks for watching, and hopefully now you understand a little bit more about RLC circuits and what it means when we're talking about resonance or a resonant frequency in an RLC circuit.